looking at probability of compound events. So far we've been looking at probabilities of single events. If I pull one card out of this deck of 52 cards, what's the probability that I get a red card, or the probability that I roll one die and I get an odd number or a prime number, any of those kinds of things. So you've also looked at the probability of getting one thing or another. So either winning a raffle ticket or cash, where you added those two probabilities together. What was the probability of getting a raffle ticket? What was the probability of getting cash? The probability of getting one or the other, you would add those two together. In this lesson, we're going to start to look at what's the probability of getting one thing and another, or that both of those things occur, such as flipping two coins or spinning a spinner multiple times. So, way back in chapter 1, you met Chris and her older sister Rachel, who made a system for determining which one of them washes the dishes each night. Chris has been washing dishes much more than she feels is her fair share, so she has come up with a new system. She proposed to Rachel that they get 2 coins, and each day she and Rachel will take a coin and flip their coins at the same time. If the coins match, Chris washes the dishes. If they do not match, now I'm saying it wrong all the time. If they do not match, Rachel washes the dishes. Rachel thinks that this is a good idea and that her little sister is very silly. She thinks to herself, since there are 2 ways to match the coins, heads and heads, or tails and tails, the only non-match, heads and tails, then Chris will still wash the dishes more often. Ha! Do you agree with Rachel? Why or why not? You've had some time to look at this. I'd love to hear some thoughts. Yes.
I think that Rachel would now wash the dishes more, because you have to have one coin roll something, and then it has to be the same the next coin, but with just one, it can just be 2 different things.
Okay.
So it feels like there would be less of a chance that it would roll both.
Okay. That's fair, yes.
So, like, since Rachel, he has to get them both to match, and Chris, he has to get them.
Oh, you got to talk slower for me. What?
Rachel has to get them both to match, and Chris has to get them, like, to non-match. But I feel like it would be the same amount of, like, percentage of washing the dishes, because he has to match them, and he has to get them unmatched, and they can always, like, I don't know how to explain it. I just feel like they're the same, they're like 50-50.
Okay. So you believe that this is a fair way of doing it. Okay. Any other thoughts? All right, so that was a matter of opinion. Does it matter if they flip the coins at the same time? That is, does the result of one coin flip depend on the other coin flip?
No, they're each independent.
They are independent. So, no. Each coin flip is independent, which is important. So I'm going to teach you how to make a table that'll give us all the possibilities. So let's make a table like this. And I'm going to make the ones across the top be coin 1. I'll mark that C1. and I'll make these C2. So for coin 1, what are the possibilities? Heads or tails? For coin 2, what are the possibilities? Heads and tails. So here this would be heads and heads. This would be tails and heads. This would be heads and tails. And this would be tails and tails. So the question becomes, is Rachel correct? Does this method give her an advantage, or is it a fair game? So what's the probability that, let's see, if the coins match, Chris washes the dishes. So what's the probability that Chris washes the dishes? Well, how many times did the tosses match? 2 out of a total of how many? Out of 4. So that's 1/2. So the probability that Rachel's going to wash the dishes, there are two possibilities where it doesn't match out of 4 total possibilities, is also 1/2. All right, so a quick reminder for anyone who might not know the rules for rock, paper, scissors. I would imagine that almost all of you know, but just in case. So at the same time as your partner, you'll shake your fist 3 times, which doesn't sound right. Sounds like you're doing this. I'm like, no. And then display either a closed fist for rock, a flat hand for paper, or a partially closed fist with 2 extended fingers for scissors. Rock beats scissors because rock blunts scissors. Scissors beats paper because scissors cut paper. And paper beats rock because paper can wrap up a rock. If you both show the same symbol, repeat the round. All right. Now, while both players are making their choice at the same time, this game has 2 events in every turn. What are the 2 events? Well, the 2 events are player 1's choice and player 2's choice. So if you and a partner are both going at the same time, does your choice affect your partner's choice? No. And again, they are independent. Each person decided themselves what they were going to do. So, as we've said, these 2 are independent of one another. Because each person decides for themselves what they're going to throw. All right, so let's determine all the possible outcomes of a game with rock, paper, scissors played by two people. We'll call them person A and person B. Be sure to include the word and. All right, so one possibility would be rock and rock, right? And for ease on this, let's say that person A is the first person and person B is the second person. So what's the outcome for that? What's which player wins? Yeah, it's a tie. So if person A throws rock, what's another possibility for person B? Scissors. Who wins this one? Player A. And then you can have rock and paper. Who wins that one? Player B. All right, well, maybe player A doesn't always choose rock. Maybe they choose scissors sometimes. Well, player B could choose rock. Who wins then? Player A. We could have paper and paper. What happens then? It's a tie. And we could have paper and scissors. Who wins then? B. And then we could have player A choosing scissors. So if it was scissors and rock, rock wins, so which player is that? B. Scissors and paper. Who wins that time? Player A. And then scissors and scissors. Which would be a tie. Is this a fair game? Yes. What's the probability that player A wins?
1/3.
It's 1/3. Why is it 1/3?
Because there's 3 out of 9.
Yeah, he wins 3 times out of every 9. What's the probability that B wins?
1/3.
Also 1/3. They win 3 times out of every 9. And what's the probability that there's a tie? Also 1/3. Now, when you're actually playing, just real quickly, does it feel like it's 1/3 tie, or does it always feel like there's more ties than there are? It always feels to me like there's more ties, and I think that has to do with human nature more than anything else.
Yeah, I noticed most people usually go rock first. Just
Well, there's a really funny Simpsons episode years ago when Bart and Maggie were trying to decide something. They were going to do rock, paper, scissors, and Maggie thinks to herself, oh no, Lisa, not Maggie. Lisa thinks to herself, poor poor Bart, he always chooses rock. And Bart's thinking, good old rock, nothing beats rock. And of course, he does rock and she does scissors, and he's like, oh, why do I always lose? Anyway, so a little bit more about independent and dependent events. So, two events are independent if the outcome of one event does not affect the outcome of the other event. For example, if you draw a card from a standard deck of playing cards, but you replace it before you draw again, the outcome of the two draws are independent. Two events are dependent if the outcome of one event affects the outcome of the other event. So if you draw a card from a standard deck of playing cards and do not replace it for the next draw, then those two events are dependent, right? Because you've taken that card out. There are fewer cards, and whatever that card is, it's not available anymore. So those are dependent events. So, page 3. One of the things that'll be on our next quiz on this unit and on the test will be things like this, where you identify, are these two events dependent or are they independent? So flipping a heads on a quarter and then flipping another heads. So if you flip a heads and then you flip again, is that second flip dependent on what you got the first time? No. So these are independent. The fact that you got a heads the first time doesn't change what your probabilities are the second time. All right, how about this one? Picking a blue marble from a bag filled with marbles of various colors, not putting it back, and then picking another marble. That's dependent. There's one less blue marble and there's one less total marbles, right? Gentlemen? Thank you. All right, this one you may not know as much about. Selecting a player for your fantasy football team in the first round and then selecting a player in the second round. Pardon? I didn't hear. Yeah, it's dependent.
Because now you can't choose that same player.
Exactly, you can't change that same player. Also, unless you're playing in a one-man league, some other people have picked as well, and you can't pick those players. How about rolling a 6 on a number cube and then rolling another 6?
That's independent.
That's independent. Each roll is independent. So if the first event changes the sample space for the second event, then the two events are dependent. If the first event does not change the sample space for the second event, then those events are independent. Okay, questions about that? Okay,